Okay, so what we're gonna prove now is that basically, if you have it that the second derivative is positive and um, it's positive on some interval I containing a, then the tangent line to the graph of f at that point lies below the graph of f. So what does this look like? So basically you have something like this. You have some curve, and basically the second derivative is positive, which means that it's concave up. And everywhere where it's concave up, if this is a, the tangent line at a lies completely below the graph. So if you have some other point where it's concave b, this tangent line of b is less than the graph at that point there. Right? So this value f of b will be greater than the tangent line value. Let's call it L of b. That's the tangent line value at b, where this is the tangent line at a comma f of a. Yeah, so again, you want to prove that the function value at b for any other point on the interval is greater than the tangent line value at that b for any other point in the interval I. To do this, we say let b be some other point in I. And now b is some other point in I, and I want to condition on exactly where b is in a second, because it's actually a little tricky how we get this inequality. So let b be some other point in I. We know by mean value theorem that there exists C between them, between A and B with. And I don't know what the relationship is really between A and B. I don't know which one's less, right? B could be over here. Okay, and then you still have the relationship correctly. You still have that the curve is above the tangent line at B. So I'm just going to say between, and then we're going to see how that changes. So we know by mean value theorem that there exists C between A and B with the derivative at C equal to f of B minus f of A over B minus A. And what I'm going to do here is I'm going to get an expression for f of b. So I'm going to solve for f of b. So I multiply by b minus a on both sides. I'm going to get f prime of c times b minus a. And then I'm going to add f of a on both sides. And what that allows me to say is that this is f of b, this whole thing on the left. And I want to show that f of b is going to be greater than a certain value. So this is f of b, right? That's 1. Now let's get an equation for the tangent line. The tangent line at A, right? This is A. This is the tangent line, this green line now. And you want to get an equation for that tangent line. So what is that tangent line going to look like? Well, we know y minus y1 is equal to mx minus x1. I have a point. The point is a comma f of a, so it's y minus f of a. M, let's think about m for a second a little bit. X minus a. Right? Now, what do I have here? x1 is a, right? Because this is the x value right here. Now, m. What is the slope of this tangent line right here? Well, we should really understand that it's f prime of a. And then this I'm just going to call L of x. And I could write it as a function. The tangent line, right? L of x is the tangent line at a comma f of a plus f of a. And we could see that there's some similarity here, especially when I want to find out what that tangent line is at any b. So when I plug in b, I'm going to get b for x, I'm going to get b minus a plus this. And now I have two nice equations that I can compare with one another. So I could have this one here. This is the equation of the tangent line at b. This is the value of the tangent line at b. And then here I have f of b, the value of the function at b. So I'm, again, at the end of the day, I want to show that f of b is greater than L of b, right? But that makes sense that this is going to be greater for a variety of reasons. So the first thing, right, let's look at this here, right? If we remember, right, that we have it that the second derivative is positive, right, we know, so let's write over here. So let's forget about looking at this for a second. We know f double prime is positive on I. This immediately implies from the first derivative test that f prime is strictly increasing on I. And then that means basically that it depends upon the relationship between C and B. I was talking about C is between, right? So if it's the case that you have it that, let's say if A is less than B, then f prime of A is less than f prime of B. And if that is the case, what you will have is that if I multiply by b minus a on both sides, right, of this equation, or better yet, if a is less than b and c is between them, then you have this. And then that means, let's get the better one, f prime of a is less than f prime of c. And that's the key one that you really want, right? I mean, it is true, this is true, but we don't need that one now. That's the one we need. If this is the case, if a is less than b, so then that's this situation where b is over here on the right of a. If that's the case, right, then we know that a prime is less than, f of a prime is less than f prime of c, right? But then what this will imply immediately is that since it's the case that a is less than b, b minus a, right, is greater than 0. So when I multiply on both sides by b minus a here, right, in this equality, I get f prime of a times b minus a is less than f prime of c times b minus a. And that's because b minus a is positive. Otherwise, that inequality would have flipped the other way. And then from here, you can just add, and it doesn't matter whether f of a is positive or negative. You add f of a on both sides, and you get your result. Because on the one hand, on the right-hand side of this equality, we should see that it's this. Right? The right-hand side is f of b. This is f of b. And then on the left-hand side, you have L of b. And this is what you wanted to prove. But that's if A is less than B. Now, my question is what happens when you have the other direction, right? So let's investigate that question now. Okay, so if B is less than A, right? Well, let's go and let's look. Let's write down what we have so far. We have what? Let's see. We got this equation and this equation. And I have that if it's the case, so let's go back. If B is less than A, then the C is between these two. So it looks like this now. Then, right? But then that means that you have f prime of C less than f prime of A. Because why was I able to conclude that? Let's write a step again. So since f double prime of A is positive, f prime is strictly increasing. Right? Again, same logic. Okay, increasing on I. And thus, therefore, since we have C less than A, f prime of C is less than f prime of A. Now, if you look at this again now, I know that from this fact, B is less than A, that means that B minus A is less than 0. Therefore, when I multiply by B minus A of both sides of this equality, it flips the other way. And I get this relationship. And then again, adding f of A on both sides changes nothing. And I have again I have the inequality that I want. Because now, again, this right-hand side is L of B, and the left-hand side is F of B. And I'm done, because now I've shown it in all the cases, okay? And the key thing here was to notice that the inequality flips when you have the other case. B is any other value in the interval. And there's only a few cases. B could be less than A, or B could be greater than A. But in either case, you see that the function value of B is greater than the tangent line at B. And that completes your proof.